Yeah, okay. Okay. That's all right. So I want to start off first acknowledging a super team of people who I work with. Probably I like to say that my greatest asset and my greatest skill is bringing in really superstar people to collaborate with, work with. You can see all of them here. I had to stagger their photographs because of, there we go. Sorry, it's clouding up my screen a little bit. But just wanted to acknowledge each one. Apologies. There's an unfortunate Zoom sharing doc that is getting in the way here on my screen anyway. So wanted to acknowledge everyone. Rob Simmons, who's in the room here with us, shepherded and got passed some excellent legislation which will facilitate Class 6 permitting in the state of Utah. And Rob and John Bosman and others are working on that right now to make that happen. We would be the third state, Utah would be the third state to gather that. Palash, who works primarily with Professor Dev and others on CO2 capture, you're becoming the go-to guy on direct air capture, which is one of the new things that I'm really pushing hard on. Then I want to acknowledge rock mechanics, and all of these descriptions of each individual are just a snippet of what each person does. It's not their full portfolio. Saying Eric Edelman works only on rock mechanics is really just short of what's really going on. Likewise, Carlos in petrophysics. Noam also at geomechanics. And Ting does so much more than just quantitative risk assessment. She's reactive transport. She's PI of a new $10 million project. I'm going to highlight her on that. You're going to blush in a moment. So she's on the next slide. Then induced seismicity. In fact, I'm going to branch out today and talk about an old induced seismicity case study, because I've presented the summary of the projects so many times. I just wanted to talk about some old work that we did years ago. It's something that I want to launch with Kevin. And Dan Stout is probably coming back. Those of you who remember Dan is probably going to come back for his doctorate, and I think we'll tackle this problem again. But in case, Aaron Meyer with atmospheric monitoring, working primarily in atmospheric sciences now and in the private sector. And then Felixia, our newest addition, she's just super awesome and leading a Western States Justice 40 working group that is just launching now, and it's going to make a huge difference in the groundwork for the Western US. Also working with Tom Cook, not shown here, and a super fabulous data management tool, along with Dr. Xu, who is what they've put together is spectacular. And then can't forget Nate. Nate, are you online? Skipping class. Oh, okay, skipping class. Yes,
he's here. We're trying to figure his situation out.
He's I've got stories, but I won't launch into them because we need to talk about some science here in a minute. Omar Bekele, one of Ting Xiao's advisees, he's taking my hydrology class this semester, and he's just a super kid. He really is. Just thinks all the time. When I walk into class every morning, he's talking about the science, the work with his Cole Chirico, who's another student in the class. And then Xiaoming has just launched a new machine learning working group in our group, focused explicitly on machine learning, big picture unconventionals, but morphing into CO2. And then Federico, Nate's Ph.D. student starting in January in his degree programs, working with us for over a year. And I mentioned Lei earlier. Lei, what you guys are doing, Lei's in the other room, is just fantastic. And then last but not least, ZD, who's working on chemomechanical coupling, which is a problem that has been not addressed by hardly anyone. So it's a pretty new topic. Oh, and I didn't mention Eileen Zabrowski, master's student working on CO2 driven EGS. She's focused on the EGS system, Roosevelt Hot Springs right now, and she's about to inject CO2 simulation wise into the model. So now I wanted to highlight Ting, tried to say Ting Shao at the same time. Dr. Shao, she is PI of her newest and largest project in a lot of time. Oh my, what has happened? Good. Is it okay?
Yeah, I had to, for some reason, I had to reclaim host to let people in.
Okay.
Very odd. So I'm going to make you host again.
Oh, no, you don't need to. It's all good. I think we're good. Yeah.
Okay.
Okay, so you can still see the screen though, right?
I can't anymore.
Oh, well, that would...
So, which is odd. So I need to, I'm going to make you host again. That's odd because I should be able to monitor who's entering the waiting room. Here, I'm going to make you host again, Brian. I'm going to make you co-host. That is probably what went wrong.
That will work. Now would have been the opportunity to tell my Halloween mask story.
Okay.
Okay.
There weren't too many people in the waiting room, but Nate was there hanging out.
Hi, Nate.
Hi, I'm here. Thank you.
Well, now that Nate's here, we can get started. So,
Oh God, don't put it all on me.
it's a joke. So I always do that. Now, can you see the main screen, or is it again the speaker share?
It's the speaker share again.
All right. How about now?
Good, perfect.
All right. So now we're seeing the speaker share. Oh my goodness sakes alive. Ting is just getting interrupted, aren't you, Ting? Apologies, everyone. Okay, we will get there. One more time. Yep. I was looking for it. It's on this screen. Well, I'm trying, but it's the one thing. Oh, the mouse is not showing up there. It's only showing up on this side. You know what? Those in the room are just going to have to see the small version. So you can slide up closer if you want to see it, but everyone online can see this nice large photograph of Ting, right? Because she must be honored in this case. $10 million project focused on the Uinta Basin, which was the subject of my PhD dissertation 30 years ago. And definitely more modern, better data that Ting and team are gathering right now for detailed analysis of the commercialization potential, CCS commercialization potential, coupled with the Bonanza power plant. Rob and Ting and others have been really hustling Bonanza to come on board with this. Milestone has been well, we won't talk about Milestone. Lots of industry partners who are really doing some helping Ting put together a fantastic project. Two other projects that were just starting but haven't even. Ting's been negotiating the carbon safe phase 2 in Uinta Basin for months now, and it's finally underway. Two projects that are still being negotiated by their leads, that is ASU and Fervo Energy. Hopefully in the next couple of months. Fervo is the energy lead. I'm the CO2 storage lead in one context. We have multiple CO2 storage leads. So anyway, so just some great projects. Okay, let's talk about EGI's field project portfolio over the last 10 years. So I'm finally 15 minutes in getting into the what I'm here to talk about. RMCCS, I'd like to talk about that because it was Northern Colorado, really fantastic project, drilled a 10,000 foot strat well and characterized the daylights out of that site. Likewise for the Aneth site, which now we're resurrecting Aneth for a new project with Arizona State. San Juan Basin, Aneth was enhanced oil recovery with CCS. San Juan Basin was enhanced coal bed methane with CCS. That was back in 2010. Then Sac Rock enhanced oil recovery with CCS. We're still working on those data sets, and we're resurrecting, like we mentioned, the Aneth EOR data set as well. And two ongoing projects include the Farnsworth EOR project that ends this year. No. Well, it technically ended this year. We did secure a no cost extension until July of 2024. It will wrap up. The only remaining task for that is fourth vertical seismic survey, along with the final report, of course, and then Paradox unconventional play. That will finish in 2024. It's not a CCS project, though. It's a unconventional oil play project. Right. What I'll talk about in terms of science is the SWP Southwest Partnership Project and its Aneth field. This is the one that's ongoing with Farnsworth. This was funded at $88 million over a period of 22 years now. And we have the SWP itself has a higher H index, that's a publication record, than any of our faculty in civil engineering. But of course, when you have a 20-year project, it would get tenure, right? I mean, it's injected well over 1 million tons. And again, we're on our 4th VSP survey, along with conventional 3D seismic imaging and gravity, magnetism, surface LiDAR. We threw the kitchen sink at this project, and it's one of the best, I think, if not the best, commercial CO2 storage data sets in the US. And Felixia and Tom are focused on that data set first, 15 terabytes of data cataloged for future analyses. But I will talk about phase 2 project, which is in the Aneth site in southern Utah. SWP is now succeeded by the Carbon Utilization and Storage Partnership, which is now 15 states instead of just the 6 southwestern Four Corner states. It's now 15 states, and not a major budget, only about it's less than $5 million per year, but it does provide one heck of a data set for, again, commercial characterizing CCS potential of the Western US. And then this is a project led by New Mexico Tech, San Juan Basin Carbon Safe Phase 3. It's kind of a sister project, a team's new project, but focused on the San Juan Basin, which, hey, we got there, EGI got there first. We carried out an injection test in the San Juan Basin over 10 years ago. So they're always following up what we're doing. So we lead, EGI leads the way on this. So focused on, we've got a new project as well with Enchant Energy. So there is 2 separate initiatives going on in San Juan, but I'm not here to talk about San Juan. I'm here to talk about CCS and induced seismicity in southern Utah, which I first gave this talk 10 years ago, and I resurrected it, updated it, and wanted to present it again because how many of you have heard? I know Ting's heard this talk before. Anyone else heard this talk before? Yeah, this is it's an oldie, but it's a classic. It's from my greatest hits. Okay, it's not like it. So what is microseismicity? And I do want Kevin McCormack. Are you online? He may not be online, but Kevin McCormack and Noam Dovori are both focused on induced seismicity, especially Kevin. And like I mentioned earlier, Dan Stout might come back and work on this. And that's another reason why I wanted to talk about it, to kind of resurrect it. I've used that word resurrect like 8 times now. I apologize. Bringing it back to life so that can really think about it moving forward. So microseismicity it's a critical aspect Macro seismicity is especially critical, but the first time a major earthquake seismic event occurs associated with a CCS project in the US, it's very possible that the industry will end before it starts, if that happens. So our most major focus in all of our CCS projects has been characterization. That's why we have three rock mechanicists, 3 geophysicists in the EGI CO2 team to focus not exclusively, but explicitly on induced seismicity. We determined in that ANF injection project back in 2008, 2009. So it's 2008 is when it was ongoing. It ended in 2010, but started in late 2007. I'll get into that history in a little bit, but microseismic is something that has become a major focus. So how often does microseismicity occur? So, Jen, you can still see my screen, okay? You now see a map of the US? Okay. All right. So you can see this is an animation that had students put together back in 2011. I had them gather all of the measured. Okay, November 27th, 2019.
Oh my gosh.
On multiple subbasins. So does gives us.
Let's get rid of that. You don't want to hear about multiple subbasin models. Okay, let's pull this back up. Yeah. Let's see if I can set it on a loop. Way back.
This is natural microseismicity.
Okay, November 27th, 2019.
Why is it doing this? Go away. Oh, I see. Yeah. It says repeat all. I wonder. Okay.
Repeat what maybe this previous.
Yep.
You put the repeat all.
Okay. Just going to show this quickly.
That it's 1986, 1988, 1991. You can see that the number of events are increasing over time, right?
No, that's not the case at all.
This reflects installation of equipment to measure, right? What we discovered in the ANF field in particular, down here in southern Utah, is that events were happening every day. And these were induced events. These reflect, to answer Rasul's question, these reflect both natural and induced events. You can see up in upper New York and Canada, Quebec, that there's a boatload of events, but it's not like the San Andreas. You got the San Andreas over here. You know, most of those are natural events. Up in upper New York, it's solution line. In Pennsylvania, you have some clusters over here associated with coal mines. Utah, you've got naturally, this basically reflects the distribution of the Wasatch and the Uinta Mountains, the Wasatch Mountains, the Uinta Mountains. The Uinta Mountains being the only east-west trending mountain range in the US associated with rotation in the Colorado Plateau. A lot of legacy seismicity associated with that. But oil field, November 11th, November 5th, 2011, magnitude 5.4 earthquake. I was sitting in my father's living room when that occurred. How many of you have ridden a subway before? My father's condominium felt like riding in a subway because we were 30 miles from the epicenter, and it was quite the ride, so to speak, due to saltwater injection. Saltwater injection, 8 miles 8,000 feet below the surface, but the hypocenter of that event at 15,000 feet. So it becomes a key of understanding in that case, and in all of these cases, understanding the hypocenter, which is the three-dimensional location and its actual origin. Okay, Kevin and Noam and others talk a lot about the phenomenon that Mark Zobak and his group at Stanford laid out, and that's critically stressed faults. Most of these events, a lot of them anyway, could be associated with critically stressed faults. And then what injection does of fluids and withdrawal in some cases is change the state of stress sufficiently to trigger those critically stressed faults. So, but I wanted to make sure that some of the maps that you see out there reflect locations of seismometers effectively. And it's more instrumentation than it is actual events. I would say that if you were measuring actual events, that you'd see fairly set for on the San Andreas and places like that, you'd see a fairly even distribution of events across the US. They're very widespread and much more common than one might think. Oh, why is it showing my MATLAB screens? I should have cleared out everything. Come on.
That looks good, Brian. That's great.
Okay, you have the screen?
Yeah.
All right. I want to talk about some other examples of induced seismicity. Get back to Rasul's question about natural versus induced events. What we've learned from those induced events, which is really what we've been focused on a great deal in the last decade at EGI. So monitoring induced seismicity, it's a critical part of EPA Class 6 applications, as Rob has laid out in his summary of EPA policy for injection wells. And it's all under the framework of monitoring, verification, and counting MVA. 50-year post-injection monitoring period minimum or standard default, with a heavy focus on measuring any induced events. But what we've done is mapped out pressure fronts, and then we measure the best proxy for induced seismicity is those changes in pressure, because it's changes in effective stress. And then if you have state of stress, which again, Kevin, Noam, and others have been explicitly focused on, you can then start to correlate the relationship between pressure changes and induced events. And what we've also done is attempted our best to interpret fracture flow directions. One of those ways of doing that is to evaluate anisotropy in shear waves. So you measure seismic activity, you measure pressure waves, P waves, S waves, and examination of anisotropy in shear waves can help infer the direction of permeability and therefore the direction of fractures, which is not something that we've started on yet in the new projects, but we focused on this a great deal in previous projects. Something else we've not really focused on a great deal in past projects, but is now getting a lot of attention from, again, our rock mechanics group, I'm Kevin and Eric, and then also ZD and others, is the stress field and how that's evolving over time. And then Kevin in particular has been examining fault activation and growth. And he just published a paper on that in the San Juan, for the San Juan Basin this past year. And our ultimate goal is microseismic events are small enough events that they're not felt, but they are measurable. But we want to mitigate those as well, minimize the risk of those turning into larger events. So, all right, some examples to get to the point of induced seismicity. Probably the most famous out of all of these, at least in my little segment of the scientific community, is the Rangeley experiment. My PhD advisor was the lead hydrologist on that. This was in 1967, so that's a long time ago. And ironically, it's not what put him on the map. he did some great things with using temperatures to evaluate permeability. But then he extended his reach into seismicity, and what they did, he and Raleigh and Breedhoff, they cycled injection of fluids at in the Rangeley field and evaluated
Correlated events to fluid cycling. So go to that. And
the Rangeley field is an enhanced oil recovery project. Couple thousand meters, about 5,000-6,000 feet depth. Injection pressure about 8 megapascals. And you start thinking about that in terms of noise, connecting the dots with respect to CO2 properties, and it's an ideal supercritical CO2 injection scenario. Not ideal, but certainly worthy of analysis. But this was only water injection. CO2 is very compressible, even in supercritical state, but water is nearly incompressible. So the pressure that you induce with water is pressure that's very much felt, and it starts to take the weight of the overburden stress and can relieve those faults, if you will, if they're critically stressed, which is what's happened there. Water injected for EOR since 1957. Now CO2, the past decade, CO2 plus CO2 has been injected. Again, close to a couple thousand meters depth. A year after injection began, pressure built up to 29 MPa, about 15 MPa prior to water injection. Seismometers 80 kilometers away detected seismicity in 1962. Principal directions of stress. One of the interesting things about this is in the Anna field. I'm going to talk about this in a little bit. I just want you to remember this slide when we come back to I start talking about the Anna field. Okay? Because, and specifically seismometers 80 kilometers away in vernal detected seismic events. Key point for later on. So this was the Weber sandstone right below the Park City formation. And this is again Raleigh et al., Raleigh, Breedhoff, and Healy, 1976, published that paper. They, at that 2,300 meter depth, cycled, come on. Yeah, there we go. You can see water volume injection and the number of earthquakes induced. So they deliberately cycled up pressure and then watched events develop afterwards. The last pressure pulse led to this last series that I mentioned in 1967. So the entire experiment lasted over 5 years, but specifically they focused on these, and they were deliberately cycling these injection rates, which is, you think about it, it's kind of a gutsy approach to deliberately induce seismic events, but they also didn't realize the magnitude of those events and the sheer number of events that would be induced. And we found later on in the Anna field that we have similar phenomena going on, just much smaller events. These were fairly sizable. Okay. So intentional fluid cycling revealed a critical fluid pressure threshold. Again, critically stressed faults. Zovac and then his students and group, McCormack, Dory, all these kids, these two kids who are now here at AGI, really helping us understand some of our current projects, including Ting's big project, Uinta Basin Carbon Safe. These results will be really critical for that. Another example, the Bohai Basin in China, 4 kilometers depth now. This is not localized long faults. So I wanted to raise this example because every example that was on that slide, a tabulation table that I showed earlier, is associated with faults and likely critically stressed faults. Bohai Basin, not long faults, but rather due to locally high fluid pressures in low porosity permeability strata. How is that connected to us? The Paradox Basin. Paradox Basin and its unconventional shales, very low permeability except for fault and fracture permeability. And so we do have, in fact, we lost, well, the field operator Zephyr lost a well due to overpressures that developed in low permeability fractures within low permeability strata. And that has impacted our EGI CO2 budget by too much. So
created a lot of uncertainty for us. But a similar type of analysis.
another one, this is really interesting in northern Italy, a natural earthquake. Also want you to remember this. So first thing I asked you to remember was detection of seismicity in Vernal from Rangeley, 80 kilometers away. Second one is this natural earthquake, another phenomenon that happened at the Anna field that I'll talk about in a few minutes. 5 kilometers depth. The natural event released CO2, and that CO2 was pressurized enough that it ended up inducing thousands of microseismic events, and you could track. And the
Authors here, there's a graphic.
could track distance away, tens of kilometers, these events. So you could track the CO2 migration by tracking the microseismic events. They imaged the CO2, using seismic surveys, they imaged afterwards and also used monitoring wells to determine where the CO2 had migrated to. But they knew in advance because of this migration pathway of microseismic events. These are all small events. Magnitude 1 less, -1, actually negative sub-zero. Use that in terms of
Magnitude before, but flow path was identified by those seismic events, which is
just really a different microseismicity, emphasize micro, very good for characterization and monitoring in terms of characterizing where our faults, where our flow pathways, like in the Italy example. So induced seismicity at the Anna site in southern Utah. Now I'm going to bring up those two
examples that I mentioned earlier.
Anna's project, injection still ongoing. That field was operated by Resolute Resources, natural resources in the teens. It's funny, you know, we don't call it the teens now. Back in the early 1900s, it was called the teens in the 20s, and we're now in the 20s, but the teens weren't called the teens in this century. But in the teens, CO2 has continued injection, but our monitoring focused on just 292,000 tons. And San Juan Basin, we literally bought for $5 per ton. Can't get that now, but in 2007, I literally purchased 75,000 tons of CO2 for $5 per ton. We can only successfully inject 18,400 tons because of cold swelling. But the Anna project, really successful. And
We continued that with the Sac Rock project and then also the Farnsworth project. I'm going to focus on Aneth, and let's go here. Skip right up ahead.
so Anna Field, southeastern Utah, San Juan Basin here, the edge of the basin and range, you can see by the edge of the topographic shift here. So we're up on the Colorado Plateau, but right next to that basin and range, which is expanding. But what's critical here is that with the Aneth site, I run this, so this is the San Juan Basin, but all of this is the Paradox Basin. You can see the boundary of this.
Can you all online see my mouse moving around?
Yeah, we can see it.
Okay, so right over here, this side of the Paradox Basin in Colorado, there's an area called the Paradox Valley, and it's a saltwater, water injection site. And so Rick Alice, the state geologist back in 2007, said,
you know what you should do, BJ, is put in an array of passive seismometers to detect energy from the Paradox Valley, because they have seismometers there, that injection operation. And you will see that energy coming across the border into the Anna field. And you can use that to map out the geology. We thought, oh, okay. So we got the funding together, got a 60-level sonde array installed. I'll show you photographs that being installed in just a moment. And we never saw a single event coming from Colorado. Okay, we wanted to get capture those events from 80 kilometers away. Okay, that's where my point from earlier, vernal and Rangeley, come into mind. And that was in part why Rick had suggested that. Locate the detection well, the monitoring well, such that you can capture that energy. We never saw a bit because it was swamped by the infield energy. Swamped. Okay, it's very noisy. The resolution of the array wasn't that great, but it was good enough to detect thousands of -1, -1.5 events that were ongoing. This field established in 56, water flooding in 61, and CO2 flooding initiated in 85, turned off, but then restarted in 2006. And that's when we came on board and started monitoring. So, and we'd actually offered Resolute, literally offered them $1 million to let us inject CO2 into the Permian, which is their saltwater disposal formation, but they didn't take the bait. Like, oh, we want to focus on oil and gas, not on those kind of things. And we've faced that with industry quite a lot. Utah, this is Beaver County. Rob, is this Beaver County?
No, that's Kane County.
Kane
way
County,
down there.
San Juan County.
Yeah.
San Juan County, yeah, San Juan County. Here's the Anna Field in red, in the far down here. And blowing that up a little bit, San Juan County have my favorite, like giving this talk, because I could say the bug field. I always like to say the bug field. I wish we had located our project in the bug field, because I just like saying it over and over. It's one of those words that I just like to say, oh, we went with Anna. The red circle here shown on the screen is my mouses. These are basically the location of the injection well that's responsible for induced seismicity. Here is that field. You can see the alternating, effectively 40-kilometer spacing of an alternating injection and production wells. This light white text down here is the location of our monitoring well, and that is where the seismic arrays was located, still is. Okay. It's not monitoring anymore, but injection's still ongoing. So it's the C313 SE. It's on the edge of these Pennsylvania strata, and you can see that this is, I keep wanting to say it's an atoll, but that's the Sac Rock Field, but it's a mound effectively, and located just north of that is a saltwater disposal well. Okay, so you have alternating CO2 injection and oil plus CO2 production. And then you've got this saltwater disposal well with 4 1-mile-long laterals, which makes the story very interesting. Is that geophone cable deployment in C313 SE, 60 levels, again, 50-foot spacing. These are members of the Navajo Nation Oil and Gas Company who installed this for us. We had a very, EGI, we had a very close relationship with NN OGC, and they just did some fantastic work. This was our seismograph tape trailer. Okay, go with those seismometers, geophones, and deepest sonde was at 5,600 feet, just right above the reservoir. We also use this for time-lapse VSP, so we did multiple VSP surveys. All of this work really became the precedent and the template for what we've done at SACROC, and hopefully, I know Carbon Safe Uinta will take advantage of a lot of this work that was done here and at Farnsworth and SACROC. So have the permanent borehole seismometers. They are permanent. They were cemented in. Continuous monitoring daily, hourly, actually seconds, hertz. Determined source mechanism, the fracture planes, really the hypocenter is what it comes down to. And what we found, we were looking for, anticipating. Jim Rutledge at Los Alamos led this effort, and formerly at Los Alamos, he's now in the private sector, but he was looking for, he and the team, the seismologists were looking for those events from the Paradox Valley in Colorado. But what they found was, since start of injection, monitoring started day 74, you can see these are numbers of events. So after even just a couple hundred days, you've got, these are daily events. No, these are cumulative, that's right, cumulative events. But over time, over a year's time, thousands of events basically detected. All less than 0, greater than -3, had some data gaps when the events, the power went out or otherwise. Those became important actually for interpretation later on. Jim and team, this is just a conceptual diagram showing stacking of multiples to build a good signal to noise ratio for interpretation. And then the velocity models that they interpreted a priori used to identify the location of the individual hypocenters, which then became, let's see here, you remember the saltwater disposal well over here. This is showing different events over time during the project. The red circles being hypocenters over time, but you can see that they're clustered in 2 different places. The far northwest mostly, but then also there's some to the east of there. There they are, right there. So you can see these developing over time, tracking this cumulative number of events, but they're not scattered throughout the field. Okay? Rangeley events were everywhere. Okay, and the events detected, well, they weren't everywhere. Sorry, they were along faults specifically, but we expect these to be everywhere because of the Paradox Valley. They were located along specific focal planes. And when you map those at the surface to look at the epicenters of these, you get this nice linear distribution of events. Fault 1, fault 2. So 2 very distinct faults, not seen on the VSP imaging, not seen in the high resolution 3D survey, only observed through this time-lapse monitoring of passive time-lapse monitoring. And here's the reservoir. All of these events are above the reservoir and those faults. And what's interesting about this, and being mindful of time, and you've got your monitoring well, saltwater disposal well, and then the 2 distributions. If you plot microseismic events versus CO2 injected, there's a slight correlation, but not much. Okay. Water plus CO2 injected, same story. Just really don't have much of a interpretation to make. But you look in the Pennsylvania Desert Creek Reservoir, see those hypocenters located laterally as well as in plan view and cross-section view. This is the really interesting story and the crux of the outcome. Saltwater disposal, yeah, you can still make something out of it. It's you've got volume of water injected, volume or cumulative number of events. But if you start to look at injection rates, we went back to the Rangeley, Colorado, Raleigh et al. Playbook from 1976 and plotted events per week and saltwater disposal injection rates. Just focus on the water, not the CO2. Again, CO2 really compressible compared to water. And you can kind of see a little correlation between the events and the injection well, but then what we did was we fired up a reservoir model and examined the travel time of pressure fronts. My favorite equation, Ting will remember this from her PhD exam. Nate will as well. Anyone who's worked with me, L is equal to the square root of alpha T, where alpha is diffusivity, conductivity over storage. You start to map out the travel time, T, travel time, and the distance of a pressure front. You can use that simple equation, calculate it, and it's about 50 days for it to go from the saltwater disposal well site to the hypocenters of the nearest fault. So you stagger that by 50 days, and lo and behold, you get a far better correlation between the events and the volume of water injected. So this is what I want Dan Stout to come back and work on for his dissertation, is to reconcile this in detail. Take detailed injection records, detailed event records, and then work with our excellent rock mechanicists and seismologists here at EGI to put together a much better resolved velocity model, coupled seismic and fluid flow model, to just take this really fascinating set of results and match it up. So
Great stuff. The lesson learned that, and the last point, I only have 7 minutes left. So, natural earthquake. Remember, I mentioned the natural earthquake in Italy. Okay. Here, a natural event, magnitude 3.6 in Bluff. Incidentally, the Arizona State DAC project will probably have its kickoff meeting in the town of Bluff. So, natural earthquake epicenter at Bluff, about 15 miles away. Well, in any case, 3.6, USGS has it at 3.7, UGS had it at 3.6, so I go with the 3.6. The home team, you know, and but the permeability impact of this natural event. Here you've got the epicenter over in Bluff. Here's the Anna field on this side. In circle. Look what happened after that natural event, the green line. Look at the production rates after that natural earthquake. So you heard the term, actually you younger people probably don't know the product shake and bake. Yeah, okay, shake and bake was a dish that my mom fixed for us when I was a kid. You shake the chicken up in the spices and then bake it. Shake and bake, basically shake this field and the production went up by 10–20%. Okay, that's phenomenal. That's the other issue that hopeful that the dream team of seismology and rock mechanics here at EGI, we can visit this whole data set. We didn't make enough hay out of this. And I want to come back to this and do some great stuff with it. So that's a great thing. So, all right, 5,000 events, and that was just until 2013. So that was over 3 years. And in some event rates are stable. Still 10 events per day minimum. Location still along the hypocenter, still along those faults, not previously identified. This is ripe for more work. We've broken out that SACROC data set. We've not done enough with the same data set.
Just
Fantastic. So, all right. Lessons learned. Look at microseismics. That's the basic lesson. All right, I have 5 minutes left. So, and I can be around all morning for questions, but 5 minutes officially for Q&A, and I'll take it from there. Thanks.
The saltwater injection was happening in the field itself, in Anna?
It was, but it was in the Permian. So the reservoir is in the Pennsylvanian. The faults are right above the Pennsylvanian. And so in that shallower Permian, you've got saltwater disposal. So the pressure was effectively propagating
outward from the injection laterals
Yeah.
and then causing slip on those faults. So, I mean, that's the hypothesis, right? I mean, and it's a reasonable hypothesis. We've not tested that in great detail. Dan Stout, the student who I mentioned, he came on board to study this. And that was his original dissertation project, but then he decided to chase, he got a married child, decided to go into the private sector, and he's still working for, ironically, a carbon nanofiber company. But he passed his quals, basically ABD, so he can come back and do that. But in any case, yeah, saltwater disposal. That's the deal. Any questions online?
Feel free to unmute yourself if you have a question.
Hello, Brian. Can you hear me? This is Ron Klusman.
Ron, hey, how are you?
It's been a while.
Good.
I'm not in the sequestration business anymore, but working on methane seepage from Mars. But the question I have is, are you doing any work with potential gas leakage due to the overpressuring of these injection reservoirs? Of course, Rangeley is the first one I really looked at in detail, and compared that with Teapot Dome, Wyoming, which is underpressured and totally depleted, and the methane leakage rate was about 200 times higher at Rangeley compared to Teapot Dome, Wyoming. And if sequestration is to be what we hope it will be, there should not be much leakage of methane or it becomes self-defeating. And of course, this early work is in oil and gas reservoirs where methane is everywhere and quite mobile. Do you have any comments about all that?
I do, and my first comment will be that I feel really honored that you joined today. Ron is I guess now I was about to say the grandfather of all work at Rangeley, but maybe the OG is the more modern term to use. He's Ron, you're the man. You are just, I'm just really honored that you joined today. So thank you for that, really, truly. And it's been far too long, like you said. We go way back. So the team here is specifically, and Ting Xiao, the young lady whose big picture I showed at the very beginning, and she's the PI of the big new project in the Uinta Basin. So just to the west of Rangeley. A lot of her original motivation was the methane leakage, and also Aaron Meyer, who is working with John Lynn in atmospheric sciences. They've been traveling out to the basin, Uinta Basin, quite a bit to measure methane leakage because of all the press, the PR that it got last year and the year before, and it's still kind of out there. And of course, DOE is investing a lot in reconciliation of the signatures. So there's a lot of new activity going on, but we probably don't have the sophisticated subsurface approach that you're no doubt taking with it. But we've not correlated. What we have done is taken well logs and looked at the porosity, density crossover, trying to see the presence of CO2 and methane in the subsurface, and then correlating that to the surface signatures. So we're trying to take the well log signatures and understand that crossover analysis results for detecting where is methane in the subsurface. Because there's obviously a lot of, like the Dakota, some of the formations in the Cretaceous have non-economic quantities of methane, and the thought is with some of the Uinta Basin strata is that it's the non-economic stuff that's leaking. And so if we can map out in the subsurface where the non-economic shows of methane are, correlate those to the surface signatures, then hopefully we can get a concerted conceptual model of what's happening in Uinta. But we certainly not extended eastward into Rangeley. But yeah, that's kind of my comment, is we're trying to do what you've done so effectively, and that is to correlate what's happening in the subsurface with what's detected at the surface.
Yeah, I had to use the old gas chromatography and mass spectrometry, but the newer, more modern surface instrumentations gives you real-time data. It's very portable and seems to work very well, but that kind of instrumentation was developed after I did the Rangeley and Teapot dome work.
If you are interested, I should introduce you offline, introduce you to Aaron Meyer, who I mentioned is working with John Lynn, but he's also working with a company in the private sector, and they've developed a portable spectrometer. It can be carried by hand, and I think the cost is around $5K, and the resolution is phenomenal. So they're kind of pioneering this small scale approach. They're trying to go even smaller than what has already been done, which I think is incredible, because it will really complement trying to understand what's happening in the subsurface through the well logs.
Yeah, I had used 1 meter squared flux chambers, which is larger than normally used, because I was aware of that very small scale variability, spatial variability in the flux. And those weighed about 50 pounds, so we're not very portable.
Let's definitely, I will, if you can drop me an email message, that's the same email address I've had for, literally, I guess I've had it since I was a student in '97 here at Utah. So, but regardless, let's touch base, and think you'd have a really interesting conversation with Aaron.
Yeah, my wife and I will be going to St. George for the winter tomorrow, and be there all winter, which is only 300 miles from Salt Lake.
Well, if you make it up to Salt Lake, we'll arrange an in-person, a 3D meeting, but otherwise, yeah, and I will be in St. George in the next couple months, just to get away from the ice and the inversions, the bad air quality in January. So maybe I'll see you in January, but let's talk before then and get you hooked up with our surface team, because they'd really learn a lot from you, I think. So
okay, I'll put together something when I get there tomorrow, late tomorrow, but it'll be then in a couple of weeks I can do something.
sounds great. And so again, really honored that you joined today. Thanks, Ron. Thanks so much. Any other final questions? Thanks. Jennifer, I just wanted to say thank you so much for organizing this. You're just fantastic at getting this all together and making it happen. Really grateful to you and Dr. Dave for EGI hosting this webinar, and glad I could do it in person here for a selection of the team here at EGI. And thanks, and we'll close it out. Thank you.
Thanks, Brian. Thanks, everyone.